Welcome back, everyone. Today, we're diving into an explainer on something that's literally hidden right inside our walls, tucked away in our appliances and hanging out up there on the power lines. We are tracing the evolution and the sheer engineering brilliance of the fuse. We're going to start small, looking at those tiny, everyday domestic protectors, and then we're going to scale all the way up to the massive, highly specialized safeguards that keep our entire electrical grid from going down.
Think about this for a second. How does a single dissolving piece of metal manage to save an entire electrical grid? I mean, it sounds a bit like magic, right? But it's actually incredibly precise engineering. You see, the stakes of electrical overcurrents are absolutely massive. Unchecked, they cause catastrophic damage. But as you'll see today, the ultimate solution relies on one simple, spectacular act of self-sacrifice.
Okay, let's dive right into this. Here is our roadmap for the explainer. The ultimate circuit protector. The AC versus DC divide, everyday low-voltage fuses, high rupturing capacity, and finally, mastering high-voltage hazards.
Let's kick things off with Chapter 1, the ultimate circuit protector. We'll look at the fundamental problem of excessive current and the surprisingly cheap solution we use to stop it in its tracks.
Let's unpack a really key term here, ADS, or automatic disconnection of supply. In electronics, a fuse is pretty much considered the absolute most crucial device to protect your system against overcurrent conditions or short circuits. Basically, it contains this little metal strip, and when an extended range of current flows through it, more than it's rated to handle, that metal strip gets so hot it physically dissolves. By dissolving, it instantly turns what was a closed circuit into an open circuit, entirely disconnecting the flow of power. It's an incredibly cheap, brilliant little device that actively destroys itself just to save your expensive electronics.
But before we can get into the mechanical designs, we have to talk about how the current itself behaves. Chapter 2, the AC versus DC divide.
So the crucial thing to understand is that not all electricity acts the same way when you suddenly break a circuit. When a DC fuse opens a circuit during an overcurrent event, boom, an electrical arc is produced. And because direct current is continuous, meaning there's literally no point where the current drops to zero, that arc is incredibly stubborn and hard to extinguish. To fight this DC arcing, engineers actually have to place the electrodes at a much greater distance apart, which is why DC fuses are physically larger. Now, AC fuses? Totally different story. Because alternating current naturally fluctuates, it changes its amplitude from 0 to 60 degrees in just 1 second. Thanks to those rapid fluctuations and 0 points, extinguishing an arc in an AC circuit is significantly easier than dealing with continuous DC.
Knowing how AC behaves actually makes it much easier to manage. Let's move to Chapter 3, everyday low-voltage fuses.
This category is super diverse, mainly because these are the fuses we interact with every single day. We're talking about semi-enclosed rewirable fuses, totally enclosed cartridge fuses, dropout fuses, striker fuses, and switch fuses. Let's break down how these completely different mechanical designs actually get the job done. First up, we've got the rewirable fuse. If you've ever poked around the wiring in an older home, you've almost definitely seen one of these. They're mostly used in smaller current circuits. The really neat part of this design is that it uses a porcelain base and a separate fuse carrier. You can easily, safely, pull the carrier right out of the base without even needing to shut off the main switch. Inside, it just holds a simple wire, usually made of lead, tinned copper, aluminum, or a tin lead alloy. Next, we have totally enclosed or cartridge fuses. It's exactly what it sounds like. The fuse element is totally sealed up inside a container with metal contacts on both sides. A classic example is the D-type cartridge fuse. And this is just a beautiful illustration of safe mechanical engineering. The cartridge is kept inside a fuse cap, and the tip of that cartridge literally only touches the conductor to complete the circuit when it is completely screwed into the adapter base. You can't accidentally shock yourself on it.
Then we get into fuses that do some pretty highly dynamic physical movements. Imagine an outdoor transformer on a pole. That relies on a dropout fuse. When that fuse element melts, gravity literally takes the wheel. It causes the entire fuse to dynamically drop out and swing down from its lower support. It's a huge visual indicator that it blew. Then you have the striker fuse. This one isn't just breaking a circuit, it's practically a little mechanical engine. When it blows, it produces enough mechanical force and physical displacement to actually close indicator or tripping circuits downstream.
And wrapping up our low and medium voltage circuits, we have the switch fuse. Just look at that number on the screen, 46,000. These switches usually come in units ranging from 30 up to 800 amperes, but their making capacity is massive, up to 46 kiloamps.
That is 46,000 amperes. Depending on how they're rated, these absolute units can safely break currents that are 3 times the normal load current.
Let's see how this technology scales up to the heavyweights of the fuse world. Chapter 4, High Rupturing Capacity, or HRC fuses.
HRC fuses are just phenomenally engineered. They have to be because they're designed to clear both low and high fault currents at crazy high speeds, all without needing any regular maintenance. Here is the step-by-step of how they work. First, the fuse element is taking on a fault current for a prolonged duration. Inside the casing, you have these silver and copper wires, often set up in parallel to boost the breaking capacity, and they're perfectly tuned so that only one wire melts at a time. To keep things from getting dangerously hot under overload, they use special tin joints that literally help reduce the temperature. But if the fault keeps going and isn't cleared, the element finally melts, popping the circuit open. And here is the absolute genius part. The inside of that enclosure is packed full of powdered, pure quartz. The exact split second that wire melts, that pure quartz acts as an instant extinction medium, completely smothering the arc.
Now, while they are maintenance-free, there's a bit of a catch. Once they operate, the whole fuse element has to be totally replaced. Plus, they do throw off some heat during faults that can mess with nearby switches if you're not careful. There are 2 main types you'll run into here. Knife blade type switches, which actually require a very specialized fuse puller just to safely swap out the wire on a live circuit. And then there are bolted types, where the conducting plates are physically bolted down to the base. For those, you literally need a whole additional circuit just to take the switch out without getting a nasty electrical shock.
Okay, we've scaled all the way up from your living room out to massive industrial switches. Let's hit the big leagues. Chapter 5, Mastering High Voltage Hazards.
When we start dealing with real high voltage, we run headfirst into the ultimate antagonist of today's explainer, the corona effect. This electrical phenomenon severely plagues high-voltage systems. It basically forced engineers to completely scrap standard structural logic and develop entirely specialized, heavily robust fuse designs just to survive these extreme environments.
The first brilliant fix is the cartridge-type high-voltage HRC fuse. So how do you bypass the corona effect? Elegant geometry. The fuse element inside is specifically wound into a helix shape, which successfully avoids the corona effect at those higher voltages. It also utilizes 2 parallel elements, one with low resistance for your everyday normal current and one with high resistance. When a fault hits, that low resistance wire blows out first, safely knocking down the short circuit current. The second solution shifts from geometry to some really fascinating chemistry, the liquid-type high-voltage HRC fuse. These tubes are sealed tight at both ends and completely filled up with carbon tetrachloride. You see these heavily employed for transformer protection or backing up circuit breakers. When a fault occurs and that safe limit is exceeded, the fuse element blows out. But watch what happens. Instantly, the carbon tetrachloride liquid itself becomes the arc extinguishing medium. It is actively battling and killing the electrical arc right inside the liquid tube. And finally, we have the big one, the explosive, self-sacrificing expulsion-type high-voltage fuse. These are super common for feeders and transformers simply because they're cost-effective. Developed for 11 kilovolt systems, these things boast a rupturing capacity of up to 250 MVA, which is just massive. So, they're made of a hollow open-ended tube constructed from synthetic resin-bonded paper. When this fuse blows, it generates a wildly violent electrical arc. But that arc is so intense, it actually blows off the inner coating of the tube itself. And when that coating vaporizes, the resulting gases form instantly to extinguish the arc. The destructive force literally creates the very gas it needs to save the whole system. And that brings us to the end of our journey today. From a simple little lead wire popping in a porcelain base to tubes of carbon tetrachloride, all the way to exploding resin tubes protecting our 11 kV grids. The next time you walk into a room and casually flip a light switch, I want you to ask yourself, will you take a second to think about this invisible mechanical alchemy silently waiting to melt away inside the walls just to keep you safe? Thank you so much for learning with me today, and as always, keep asking questions.